So what happens when you have here beams and shear? I understand that when you have a beam and you start to put some loads on the top of it, this beam here will be exposed to flexure, like moment, and also to shear. And this is the reason that we have the bending moment diagram and the shear force diagram. It's kind of a standard, and we understand that. There's nothing wrong with this. The problem here is when you do your design for the flexure, which means for the moment diagram that you have on the beam, you're going to be taking the point of maximum moment and design the reinforcing for it. And this is what we have been doing. The reason that we put moment at the bottom of the beam, because look at this beam here that you're testing it. You're testing this beam, they put 2-point loads so that they're going to have a nice and clear section of the beam to be only under flexure, which means under moment. And look what happened. The beam will start to crack from the bottom, like all of these cracks. We call this flexure cracks, which means cracking due to the bending moment. And this bending moment is causing tension force. It's going to be pulling the beam at the bottom in this direction. And compression force, which is going to be pushing the concrete on the top. And this is what you used to call here tension compression. So you're going to have compression on the top and tension on the bottom. Generally speaking, the crack direction is going to be perpendicular to the tension force. So here I'm expecting tension force is going to be in this direction. Tension force here is going to be in this direction. This makes sense. I understand that here I'm going to have compression force, and here I'm going to have tension force. And this tension force here is going to be causing the beam to fail in this fashion. I understand that bending moment would give me the maximum value right in the middle. This is why the very big crack happened right in the middle. This is the point here of maximum moment and maximum tension force throughout the beam. So if you go here through any point, like any section, let's say this section right here, and then you determine the tension in this location, compare it to the tension at that location. I'm sure here that this section with the maximum moment is going to have the highest tension throughout the entire beam. If you move a little bit, let's say about maybe a foot away, now tension force is going to be less than the tension force at this section. So when you go closer to the support, the amount of tension force due to moment is going to reduce. Also, when you have this simply supported beam, moment on top of support is going to be equal to 0. But when you look at the shear diagram, it's going to be the other way around. The shear is going to be max at support, and it's going to be equal to 0 at the point of maximum moment. We understand this fact from statics and mechanics of materials. So looking here at this beam, I'm going to say this beam, it has this moment diagram and the shear diagram at the same time. This beam here failed in flexure, which means failed due to bending. The bending strength at this section here was lower than the demand, the applied of moment that you put to it. That's why it failed in flexure. Now, where's the point of maximum shear? I'm going to say point of maximum shear is going to be in this zone. It's going to be this location here. This is going to be the area of maximum shear. So to me, this beam was strong in shear because no shear failure happened. Look at the beam, it's very clean. It's very good, right? I don't see here any cracks. So this person here, or this group, they wanted to test this beam in flexure. So what did they do? They did the analysis and they put lots of reinforcing here, and the reinforcing, of course, is going to be in different direction because it is going to be there to resist the shear. But they confirmed it before testing that this beam is going to be strong in shear, so no shear failure is going to happen, and the failure, if it is to happen, is going to have here at the middle of the beam where you have the point of maximum moment. So you can control the way that you're going to have your failure in the beam. Let me show you here this quick clip. We have the reinforcing that we put throughout the beam, top reinforcing, bottom reinforcing, and then we have lots of ties. These ties, they are here to resist the shear. I'm going to explain how. And this, I guess they just put the beam here reinforcing upside down because your top is gonna be where you have this two hooks. So this is actually the top of the beam. This is gonna be the bottom of the beam once you put upside down. So here, this bottom reinforcing are provided to resist the tension, which means for the flexure. That's exactly what you have here. Gonna be running this and give some comments on what they're doing. They build the beam. This is a bottom reinforcing, this top reinforcing. They have concrete. Of course, they have the formwork to do the slump test on the concrete. And they do the formwork, fill in the beam with the reinforcing. Expected failure based on the analysis, do 2-point loads. And now they start to put the loading. Now we need to look here at the cracks, where the crack is going to start to occur. This crack is going to start to occur once the concrete stress at the bottom is going to be reaching 7.5 square root of F prime C. Look at the cracks start to form. Of course, it's going to be right at the bottom. Look at these cracks. It's coming right on the bottom. If these cracks are happening this way, it means tension force is perpendicular to it.
Could you rewind just a little bit to see how the cracks are forming?
Okay, this is the beginning of the cracks.
Mm-hmm.
See this? Going back a little bit. No?
I think if you press play, there we go. Oh yeah.
Almost no cracks, very small cracks. Now all the sudden cracks here are going to start to occur at the bottom. This is where you have the maximum tension. And this is going to happen in this region. You see the cracks now is happening, but no shear cracks. Shear cracks is going to look completely different that we're going to discuss. But first we need to discuss this flexure crack. And you see they're growing up from the bottom, which means neutral axis now is going to be in this location.
Professor, I heard that you might be able to fix that, right? Using some like reinforced fiberglass
Yes, you can
as
fix it.
posture. Mm-hmm.
Absolutely. There is usually a repair. There's a way to repair it and fix it. Yes. But you know the reason that they're doing this testing because they'd like to see the mode of failure and they'd like to confirm the analysis and calculations that you're doing. We say the beam is going to fail
Mm-hmm.
at this point, whenever the moment is going to be this much, but now we need to confirm it by testing. See, this stopped a little bit and then they're going to be adding more loads. Look what happened. Cracks is growing up. Now you have more cracks, but both sides of the beam are free of cracks because you don't have any shear. The shear strength, if you like to call it, shear strength is really good and it's higher than the shear demand. Look at the depth of the cracks. Now I'm gonna stop here and this is here at the support. It's gonna start to rotate and no shear cracks. Look what happened in here in this location. It means neutral axis depth right here is getting in this location, right? How about here? Maybe a little bit down. How about here? A little bit down, a little bit down. Which means depth of neutral axis is not the same throughout the entire sections of all the beam. Whenever that you're gonna have here maximum moment, neutral axis depth is gonna be up here. When you go close to support, it's gonna be down, maybe at the mid height of the beam. Apply more load, watch for the cracks. Now reinforcing is working, otherwise this beam would have been on the ground. Watching carefully, safety glasses. Tap, we're very close from failure here. Oops, now it failed. What happened to the rebars? It's gone. Snap. Just cut them off. Load was just too high. See, the beam now is just stretched out. All the rebars. Look at the rebar, just cut. No rebars. Compression the concrete. Look at this shear section. In very good shape. Nothing is wrong with it. So, okay. Let me look here when I have shear cracks, how it's going to look like. This concrete block exposed to shear. And if you see here in this testing, they're going to be taking this head, the top head, and push it to the right or push it to the left. And look what happened. You see this crack in the top. Why? Because this is what you're doing to it. You're pushing it this way and that way. It's causing this, what we call here, diagonal tension. At the same time, you're pushing. If you guys recall the stress element, if you remember also more circle. So in this case, you're going to be pushing it to the right. Some shear failure examples, so that you know that shear failure is terrible. It's just bad. This is not flexure failure. Of course, any failure is bad, but at least in flexure failure, you see the beam deflecting and coming down. So it's going to give you some warning, lots of warning. In shear, you're not going to see lots of warning, and you're going to see now in testing. This is some shear failure examples, various pictures. Let me show you here what happened. So in this beam here, the force is coming from the underside. It's going up, it's just pushing up. And supports are right here. Now, where's the tension? You're going to say tension is given the top, compression is given the bottom. So this is opposite what you used to see. Look, when they start to put some loading, you start here to have some cracks. And they put here some strain gauges. So the strain gauges here is going to tell you, and you see the wires coming out of it to test the strain in the face of the concrete beam. Let's see what's happening. Now, at the beginning, you're going to have here some flexure cracks. The beam here is going to start to crack. And look what happened. This is here, flexure crack to here only, to here only. Once the crack here is going to start to take an angle, you know this is not flexure crack anymore. You're going to see it now. See what's happening? This is not flexure crack. Flexure crack is going to be this crack here, because the tension is going to be in this direction, right? When you have the moment, you apply any moment, you take this moment, divide by the depth from tension to compression, which is the Z value we have considered. You find out the tension force in this direction. So tension force is not coming in this direction from flexure. So this is actually the diagonal tension I was just talking about, and this is going to be the shear crack. Look what happened. You see this? This is not deflection. This is just failure. Failure started already, and you don't have enough warning. But the rebars are still there, which means this beam here is strong in flexure in moment, but it is weak in shear. Now we understand the reason that we say ties can be resisting shear, because what needs here to keep these two pieces together is just to put vertical ties here, right? If you have here enough vertical ties, this piece or these two pieces have been as one piece, acting as one piece. So this beam lost the integrity because you don't have enough shear ties. Another example here of shear failure. Cracks. Look at this again. What happened? The rebars are still in place and they're acting well, but look what happened. There is no enough ties. This is why you need to have here enough ties to keep the beam together. Look at the shear crack on the other side. Without, and look at this. This is here when you have no, let me play this again. Look at what happened on the right hand side. Right here, no ties at all. We're just missing the ties here. We didn't put them. We thought that it is enough to put the reinforcing for the tension. Look what happened. The beam is failing.
Professor,
Yeah.
we know that concrete is pretty bad at resisting strain or like tensile force.
Yeah.
Steel it doesn't perform well under shear, or is it compressive force?
The steel is good in tension compression.
Mm-hmm.
But the failure, yeah,
mm-hmm.
Go ahead.
But is it the shear force that kind of like is an end all to almost every material?
Yeah, shear is just bad.
Mm-hmm.
Almost all material is just bad. Steel is good in shear if you're exposed to a shear, but the reinforcing itself is not exposed to shear here in our case.
Oh,
But
okay.
concrete is very bad because brittle material, right? And it's very bad when it comes to shear or tension. Let me show this testing here. This testing for shear. Now, in this case, the beam is very strong in moment, which means we put lots of reinforcing, right? So we know that the applied moment is going to be less than the capacity moment. Look what happened. But here we didn't put any ties. I guess we're supposed to put ties here, right? To resist the shear. Look what happened. No ties. Do you see here any reinforcing? Nothing. They didn't put enough ties. And look at the failure. It's kind of, it's a very brittle failure, sudden failure, and it just happens all of a sudden. Nothing that you'd like to see. Another test here for some beam, small scale, very small scale. This beam is a strong flexure. There's no ties. And look at the cracks. Start here to point at the cracks. You see the crack? This crack here, this is not flexure crack. The flexure crack is going to be here. It's going to be going vertical. But once you come here, this area here, it has more shear and very small moment. And right here, right above the support, moment equal to 0 and shear is max. So actually, this is going to be the zone with maximum shear effect. Look at the crack. This is a shear crack. Here it has an angle. You don't see here lots of deflection, like in the other test that we started with. The other test, we have lots of deflection. And everybody was able to see it. So you can run away if you want to. And look at this. It is failing in shear. But you see here lots of deflection. Deflection is very small. It's just gone. Now the beam is gone. And you don't have lots of deflection. So this is going to be the bad thing about shear. It doesn't show lots of deformation before it happens. But look at this. This is now failure in flexure due to moment. Lots of deflection. So before it happens, you can escape. This is going to be here shear failure. So what happened in shear failure? In flexure failure, I'm going to put here like an arrow for the tension direction. I'm going to say tension is going to be coming this way, and also tension is going to be coming this way, right? Now in here, where's the direction of the shear? Of the crack. I'm going to say here direction of the crack. Therefore, direction of the tension is going to be like this, right? This is going to be perpendicular to the crack. So at any location, you can say, well, this is going to be the crack direction. This is roughly like this, and the tension is going to be perpendicular to it. So the question is the shear has an angle or the shear is vertical? So I'm going to take you back here and remind you is what you have studied in Moore circle for the stress element.
Professor, you mentioned that
Yes.
you can kind of like visualize when, like, you'll have a warning before the beam's about to crack. How would I kind of like see that if it, for example, in my office building, would I see kind of like the acoustical tile fall off, or how will I know?
Need to take the tiles, take them away and look at the beam and see if you have any cracks here at the bottom, like these cracks. You can see them at the bottom of the beam. If the beam is free from cracks, then you know that you're in good shape. There's nothing wrong with it. But once you see any cracks like this, you don't stay in the building.
Oh, okay, roger that.
Right?
So the same thing would go with
there.
like with parking structures that have the exposed beam.
Yes.
Right. Okay.
Yeah, and parking structures. Yes, this is correct. So let's here take one of this stress elements. We call this a stress element. If you guys recall this, that you have taken in principal stresses and Moore circle. I know that you have taken this maybe some times ago. If you take here a stress element, what happened? You have this shear, and you know the shear is going to be vertical. But usually, when you have this vertical shear, you're going to have also this conjugate shear. It's going to be also horizontal. Otherwise, this stress element is going to be unstable. So what happened? You have one shear component here, one shear component coming down, and also you have this shear, horizontal shear is going to be coming that way, and horizontal shear is going to be coming this way. These two forces is going to form here this component of the diagonal tension that I'm talking about. So if I may take you here back to this previous slide, this here explains what happened. What happened, you have one shear component going up, another shear component coming this way. So actually what you have one shear component coming this way, if I may draw it this way, and one horizontal shear component coming this way. The resultant force is going to be coming like on an angle. And this angle usually is about 45 degrees. And of course, it depends. If you have some reinforcing, like vertical reinforcing for ties, you know, we put ties this way, right? One tie here, maybe a few ties that you put in here would have been making the performance much better, right? If you put lots of ties in this way, it's going to keep these two pieces together. So if you put ties, this angle is going to change a little bit, but roughly it's going to be about 45 degrees. I'm gonna take you back here to this clip. I'm gonna take you here to this. Look at the shear. This is gonna be the shear deformation for one of the stress elements. See what happened? You have vertical component, horizontal component of the shear. Both of them will create this diagonal tension, and this is the reason that we have this crack is given an angle. So this is actually what we call here diagonal tension. And look what happened. Here's diagonal tension, and most likely this is given about roughly 45 degrees. Now I understand what happened here. I guess now I understand why this is given an angle, because the shear component, you're going to have two components, horizontal and vertical one, and they're going to be causing this diagonal tension both sides of the beam. Okay, I guess this is now clear to me. I understand what's happening here, and this also explains the reason that shear crack is going to look like this. Flexure crack, just look at the bottom of the beam right in the middle, closer to the point of maximum moment. If you see horizontal crack running on the bottom of the beam, you know that this beam is going to start to see here some cracks. But if you don't have lots of rotation, what do I mean by rotation? I mean this rotation here. This is rotation, right? The beam, the bottom of the beam is rotating, it's coming down, which means deflection here. So you know that the beam here starts to fade in flexure. But if you see no cracks at all, like horizontal cracks, and all of a sudden on the side you see a crack like this, or a crack like this on the side of the beam towards the end, when you have the point of maximum shear, you know that you cannot stay in this building. You need to get out of it right away. Here's the reason that we have these ties. Also, it's called the stirrups. And the reason that we have these ties because they're going to keep the concrete two pieces together. So if you have here one of this section, right, and then you put the bottom reinforcing, now you put the top, right? The top, you cannot just leave it like this. You need also to put a couple of rebars on the top. Otherwise, what is this stirrup is going to be hooked to? So for example, I'm going to go back here. Let's say that I start here to put some vertical rebars, and this vertical rebar, this is what we call here ties or stirrups, right? I'm going to put them like this. If you just put here just some rebars like this and you didn't hook them to any reinforcing top and bottom, now once this wants to open, this rebar here, it's gonna be just, you can just slip it. You can just pull it out of this concrete piece. Nothing is gonna stop it unless you hook it to something. How do you hook it to something here? You put this hooks and you put it like this, and then you put a rebar inside within this tie itself. And with this rebar within the tie itself, it's gonna stop it from coming down. So this resistance here wouldn't happen unless you have a couple of rebars right here at each corner. You're gonna put here one rebar, another rebar is gonna be here in this location. So without these two rebars, these ties are not doing anything to you. Now, where is the point of maximum shear? Is it right at the support itself? Code says no. Code says if this failure to happen, look, I'm going to take you also back to look at some of the failure pictures. I understand that the point of maximum shear is going to be here, right? Right on the top of the support. But when the shear happens, the shear crack happens, it doesn't happen here. It happens right here, right a little bit next to it. And if I may draw here a line, if I'm going to draw here a line of 45 degrees from this point. Why this point? Because this is the entire width of the support. If you put here a line with 45 degrees, you're going to see it's clean. This area here is clean. Why? Because when the failure happens, this piece of the beam wants to go down. And this piece of the beam is acting as an integral piece of this support of the column. This is why it is not really failing. There is no cracks here. Also look at this crack in previous lectures or previous, pictures here. Look at this piece here. Look at this. If you take here a diagonal line, this piece is very strong. It is actually part of the support. And if you want to break it, you just put pressure. It will never crack in a vertical section here, but then it says going to be doing it on 45 degrees. Okay, so good, all right. This is why the code says if you have a beam like this, right? Now you'd like to see where is the critical section for shear. Now I'm not looking here for the maximum shear. I'm looking for the critical section for shear. Where does it happen? I'm going to say go here from this point and go then angle 45 degrees. So this is going to be what? If you like to call this low, Gonna call this here 45 degrees, right? And with that, this section is gonna be part of the support. So take your ultimate shear right here at this section. Meaning, don't take the reaction, say this is gonna be the maximum shear. So do not take this reaction. No, it is not gonna be the reaction. Instead, it's gonna be that force that happens at the distance away from support. Why? Because if you go here 45 degrees, this is gonna be D, and also depth is gonna be called D. So this makes sense, yeah, 45 degrees. How about here? You can say the same. Take a line here at 45 degrees. Take a line here at 45 degrees. If this is gonna be D, this is also gonna be D. So you need to stay away at D distance from the face of support. And then at that point, you figure out the maximum shear. This is what you call here shear demand, V sub U. This V sub U. And this is what you need to design for. How about shear strength? Well, in the past, we used to have M sub U and phi m. Here also we have V sub U and phi Vn. We have also shear strength. So what do you call this? It's going to be shear strength. You want to be sure that the shear strength is going to be greater than the shear demand in this case. So we have these two cases. When you have continuity in the beam, you go D distance away from it. Same thing here. You go D distance from face of support. You don't go D distance from face of column. There's a big difference here. This is what you call the support. This is going to be the column. So I'm going to be going here D distance from the face of this support, not from D distance from the face of column if I have a situation like this. This happens a lot in bridges. But if this is not a column, this is like a vertical tie, and the whole thing here is going to be in tension. Do you think I need to take this at 45 degrees? Now think about the failure. It is true if I'd like to push this piece down, yes, the failure is going to be like this. But how about here? If I need to push this down, do you think this piece is going to stay as integral piece of the column or of this hanger? You say no. If failure is going to happen, it's going to happen right at this face of the support. So it's going to happen like this. The entire column here or tie is going to be just going up. And this beam is going to stay in place. Or this beam is going to be coming down, if you like to call it this way. This column here, let's say, is going to stay in place, and this beam is going to be just coming down this way. There is no way that you're going to see here an angle of 45 degrees. Otherwise, this angle is going to work like a ledge. It's going to be an actual support, and failure wouldn't happen. This is the reason the failure is going to happen at this vertical face or the interface between the beam to the column. Also, if I have a concentrated load that happens within this D distance, it's going to break this piece. So I was expecting, if you look here, right, I'm expecting that usually this piece is going to work as like a column head, if you like to call it this way, or column cap, right, this piece here. But if you put a big concentrated load and you put it within this D distance, it's going to break this piece. So this piece that I was thinking about is going to work like a column cap. It's not going to stay there because this point load is going to be breaking it. So actually now the critical section for shear is going to be right at face of the column. I have 4 separate cases. This is going to be usually the standard one that you're going to be using in most applications. All right. Now let's look here at the equation. I need to figure out the shear demand. How do you do here shear demand? Well, you need to find out the shear at this critical section. So you go here at this critical section, find out the amount of shear. Okay, is the shear due to dead load? You can say yes. Live load? Yes. What load combinations you use? I'm going to say use the same load combinations that we used to use in the past. Which means that you're going to be doing here 1.4 times V due to dead load, right? You compare it with 1.2 V due to dead load plus 1.6 shear due to live load. Compare the two numbers. Of course, you take the larger of the two. Okay. How about the strength? Now I know the demand, right? So this section here, or this slide, just for the demand. And this one also, it shows you where you take the point of critical shear for the demand. Now strength. The strength is simple. They say the equation is very simple. They say phi Vn is going to have 2 components. One component is going to be coming here from the concrete. The other component is coming from the steel. Now my question to you, which steel am I talking about here? Is this about The bottom reinforcing or the top reinforcing or the ties? I'd like to hear from you guys.
Ties.
Ties, right?
Ties. Yeah, from the ties. Because in beams, the shear strength is coming from the ties. It doesn't come from the bottom or top reinforcement. The phi factor is just one value. You see here what it says, 0.75. Nice. So I'm not going to have a graph. I don't have to find out the strain in reinforcing. Just phi factor for shear is going to be 0.75. So actually the shear design is much easier than the flexure design in beams. So what is VC? Strength by concrete. What is VS? Strength by reinforcing. Okay, you just add it together, yes. How about VC? Do I have an equation for it? It says yes, here it is. Simple equation. It says here shear strength equals, now this doesn't include the phi yet, 2 times the square root of F prime C. Now, when I use here this F prime C, is this in KSI or PSI?
PSI.
PSI. It has to be in PSI. So be careful about this. What is BW? What is D?
Base width? No.
This is going to be the B is going to be the width of the web, the width of the concrete beam, and this is going to be the depth from where to where? From the tension to the top compression, to the rebars, right? So the rebars, just gonna here, so we need the rebars. If it's like some box, this is gonna be the middle of it, right? To the top of the concrete, this is gonna be D. So this area here is gonna be the area exposed to shear, right? This is gonna be the sheared area of the beam. And we ignore the cover, the bottom cover, because it's gonna be cracked anyways, right? So it's gonna be the area of the concrete times the stress, allowable stress. It says here the maximum F prime C is gonna be 100 psi. When do you think this is gonna happen? At what concrete strength? Yes, I'd like to hear. At what point the square root of what is gonna be equal to 100?
10. So 10,000
psi.
PSI.
Yeah, after this, let's say that you have 12,000 psi concrete. You're gonna keep it as the square root of prime C is gonna be equal to 100 psi. So you're gonna have a limit or a cap to it, right? And then after that, you have the phi factor of 0.75. Sounds very easy, especially when you see an example and you're trying to find out the width, let's say 16 inch by, let's say 21.5 times 2 square root of, now you are done with the concrete strength. So it is not really tough. So, okay. How about the reinforcing? VS, how do you do here VS? VS has this simple equation. Now let's see the variables. AV is going to be the cross-section area of the ties. It says here total reinforcing cross-section area of the tie resistant shear. Right? How about F sub Y? F sub Y, this is the yield strength. Any yield strength, I'm going to say for the ties. Does it mean I should be able to use 2 different steels in the beam, one for the longitudinal rebars, the bottom or the top, and 1 different steel for the ties? I'm going to say yes, this happened in the past. Not anymore. Now, usually FYT for the ties is going to be the same as the FY we use, is going to be 6 KSI. Depth, you know D, you have used it. How about S? What is S? Say tie spacing. I'm going to take you here back a few slides to this one here. Now, where is S? Tie spacing, right? Where is B? Here's the depth, the width B. Where's the depth? Depth is given from the tension rebar to the compression. So what is AV, area of steel, for the ties? I'm going to say, look at this. Let me cut this section here, this diagonal section, right? And let's look here at one tie only. So we're looking here at one tie only. How many sections have you cut through? Let's say I cut through this guy, cut through this guy, right? So A sub V is going to be total cross-section area that I've cut through here. So I'm going to say this is going to be actually equals to, this is going to be equals to A sub V. It's happening. So A sub V equals to 2 times A sub B. What is A sub B? The area of one bar only. So this is going to be equal to 2 times A sub B. Why? Because I cut through 2 ties. When you cut through 2 ties, A sub V is going to be equal to this plus this for 1 tie only. You say, okay. How about in a case like this? Where is A sub V in this case? This is all happening as one set altogether. So in this case, A sub V is going to be 4 times. And I'm going to say here, cross-section area of 1 time. Which means if you cut a section right here, how many ties have you cut through? I'm going to say 1, 2, 3, 4. So A sub V equals 4 times the area of one of these tie legs.
How do we know when to use multiple cross ties? Is it
Well, are you talking about practice or are you talking about like an exam and homework? Exam and homework, I'm going to let you know. In practice, let's say in practice, you need to look at the shear and put some ties there. If you don't have enough strength and you really would like to use more tie legs, by all means, you start to add here more tie legs so that you have enough strength. So it's going to be actually up to you. As a designer, you pick and choose how many legs you'd like to use. If you like to start, I'm sure that you like to start only with 2 legs, right? Why would you put multiple legs? Because it's going to be taking time from the people working in the field. So you would like here to reduce the number of these legs. So maybe you'd like to start with number 4 ties. So I'm going to put here, I'm going to say usually start with number 4 ties. Right?
And are you saying number 4 ties as in the like size of the rebar?
Yeah. Yeah.
Okay.
Size of the rebar is going to be number 4. Right?
Got it.
We call it number 4 ties. And you'd like to start with 2 legs. It's going to be 2, right? Times the cross-section area of number 4. Anyone knows the cross-section area for number 4? Can someone read it down for us?
0.79.
To 0?
Are you sure? I know it's
0.5.
0.2.
Oh.
No,
0.2.
number 4 is
0.2
0.2 square inches. This is how I know it. So it's going to be 0.2 square inches. Now, in this case, if you just have here 2 legs, I'm going to say here A sub V, I'm going to write down here, in this case, A sub V equals 2 times 0.2 is going to be equal to 0.4 square inches. If I have a case like this. How about a case like this? If I have number 4 ties, let's just assume for a second that I have here number 4 ties in this case. How about A sub V? You see, now this is going to be number 4 ties. A sub V equals 4 times 0.2, 0.8 square inches. Okay, easy, understandable, or no? How to figure out A sub V? You look at number of legs, and then you start to do your analysis. Here, see number of legs. Here's the tie size, cross-section area for 1 tie, which is A sub B is going to be equal to this much, multiplied by a number of legs. Okay. All right. Now let's go back here. Let's go back to this slide.
Excuse me.
Yeah.
For the spacing, is it going to be measured center to center?
Yes, this is correct.
Okay.
And in a minute from now, we're going to be talking about what is the appropriate spacing. What spacing would you like to use in a beam? You can say, I'd like to use number 4 if possible, and I'd like to use maybe 12 inch on center for the tie spacing. I don't want to use 3 inch on center. Just imagine if you have all the tie 3 inch on center, how would you put your hand inside there to time? It's going to be kind of impossible, right? It's going to be very congested. Don't you agree? So you'd like to have some good spacing, maybe a foot, maybe 10 inch, 8 inch is going to be the worst case. This is going to be the smallest. But you'd like to make them as big as possible. But also the code, it has maximum spacing. You cannot just put it, let's say, at 2 feet or 3 feet. The code also has their limits, right? I'm gonna take you back here and say, just imagine here, how would you put your hand if this had been here 3 inches? Let's give you one question. Other question that I want to take you here. Where do you think that you need lots of ties? Do you need them in this location or throughout the entire beam?
You wouldn't need them for the entire beam, right? Only for certain parts?
Yeah, here's the shear diagram. I'd like to draw here the shear diagram, right? and here is the shear diagram. I'm gonna say, where is the area here of maximum shear? I'm gonna say area of maximum shear, maybe this section, right? And this section from both sides. How about the middle area here? I'm gonna say, well, shear is not gonna be that much. So if you like to play with the spacing of the ties, the number of legs, I'm gonna say here, this section and this section, area of maximum shear, you're gonna have lots of ties, expected. But this area here, close to almost no shear, cannot put that many ties. I can put maybe the minimum as required by code. Does it make sense?
Yep.
Okay, all right. Okay, now let's work here on this slide. Try to understand more the variables that I have here. It says here VS max, and then all of a sudden I see here some numbers. It's related to the concrete strength. Here's the problem. Some people are going to go here with a very small beam section, and this beam section is made out of concrete, and they start to add lots of ties, lots of legs. Now, when you look here at VS compared to VC, you're going to find out that VS is going to be too large. I'm going to take you also back one slide. You have here combination between the concrete and the steel. You don't want to go with almost no concrete and you put lots of steel and you think now the beam is going to be strong enough. So the code says the concrete is going to be equal to a factor of 2 square root of F prime C times this factor here, right? And they say the steel cannot be more than 4 times stronger than the concrete. How do I know it's going to be 4? Because here it says 8 and here it says 2, right? So the concrete is taking this many kips. Let's say this here equals to 100 kips. I'm just throwing here a number, right? If VC is equal to 100 kips, how about VS max? It's going to be how much? This is here 100 kips, and this is going to be 4 times. So this is going to be what? 400 kips max. So it gives you here a limit. So if the capacity, yeah, go ahead.
So VS max would be the 10 or the 100? I was kind of confused with what you were saying.
Okay. I said here, let's say I did some analysis, and V sub C based on this equation, I'm going to say here V sub C as an example equals to 100 kips, right? Just my analysis. My question to you is, what is VS max? How much do you think VS max is going to happen? You're going to say VS max is going to be equal to 4 times 100. Does it make sense? How do I know this? Look at the equation. Equation says 2 square root of F prime C times B times D, right? Look at this factor here, F prime C, B, D. How about here in this equation, F prime C, B, D, same equation. So what's the difference? Difference for this one here, this says here 2, and the factor here, the shear factor says 8. So if I did some analysis and this turned to be, this VC turned to be 100 kips, I'm expecting that the maximum shear taken by steel is going to be 400 kips, not more. So okay, makes sense. Yeah, there should be a limit. So in your analysis here, you're just going to be running the equation and say this is going to be the VS max. Don't go beyond that. Otherwise, people is going to be dumping lots of steel for the ties, and the concrete performance is going to be poor because you need to have concrete and steel, right? Also, they say you don't really need to provide any ties when the demand is less than 1/2 of the strength of the concrete. Not very clear, but maybe one example is going to make it clear to us. They say here, if you need some shear reinforcing, you're going to have here these 2 equations to give you the minimum shear needed. What are the components of this? It shows here a constant, F prime C, BW, S the spacing, Fy is going to be the yield strength. Look at this, BW, S, Fy, T, which means a 6K sign. So I have here 2 equations for the minimum value for steel if needed for the ties. Let's see the example, just to make it simple for us. This example here says determine the shear strength adequacy for this beam. Did you guys see this beam before?
Yes.
Okay, this is one of the examples that we have used. It gives you here the span, it gives you here the load, dead load on live load, concrete properties, steel properties. Dead load, live load, do ultimate load, 292 is going to be the one to use. We went through this before. Any question on this? This is going to be the demand, right? As a uniform load. So fine. Here is a shear diagram that we have. Here's the beam loading, span, clear span. How much is the clear span? It's going to be 20 feet. So what is the span? When I say here span, what is the span? Span is going to be distance from support to support. 22 feet. Right? So the span was given here to me in the problem. It says here 22 feet. But the clear span is 20 feet. So I'm trying to understand what does mean by center to center, which means center support to center support. And the clear span is going to be from face of support to face of support. So the support width, it could be maybe 2 feet here, 2 feet there. Anyways, the clear span is going to be this 20 feet, and the center to center support is going to be 22 feet. Means the column is going to be right here. You see the column? Here's the column. It's going to be running like this. And here's the other column. All right, great. So what is the reason that I'm going to be interested here in the clear span? I'm going to say because I'd like to go the distance away from face of support to find out the design shear, V sub U. If you want to go here the distance, it means I want you here to develop the shear diagram and then find out the shear at this location. Where is this location coming from? It's coming at the distance from face of support. How can we do this? Let me go back here one slide. The distance away from face of support. Where is this coming from? So okay, from here. So from face of support, I'm gonna go here the distance, right? Here's the distance because I'd like to do here this 45 degrees. Now I need to look at this. What are we doing here? Here's the shear demand. Take it at face of support. Take this uniform load, time the entire span, you're gonna get the reaction. So 32.12, this is gonna be the reaction. So the shear at this location is gonna be the reaction, right? This is the reaction. How about here? It's gonna be at face of support. Yes?
That 13.5 is just the depth?
Yes, I'm coming to that. Yes, you are correct. Yes. But I want to explain first the shear diagram, the values that you're looking here at. So if you take here 2.92 times 11 feet, which means 1/2 of the span, it's going to get you this reaction here, the 32.12. But this is not the shear that I'd like to use in my design. I'd like to go at face of support first. Let's go here at face of support, which means at 1 foot. How much is the shear here? You say, well, shear here, I can find it easily. How do you do it? Look at the diagram, find this out. Or, you know that the shear change from here to here is going to be equal to how much? The shear change is going to be equal to this uniform load, 2.92. Because it says here, this uniform load, 2.92 kip per foot. I said, okay, how about D distance? It says here D equals 13.5 inch. Let me go back and check. Is it 13.5 inch? Yes, this is the one that we have done early stage in one of the slide sets. And we say 16 minus 1.5 minus 1/2 inch for the tie minus 1/2 inch for number 8. This is how I ended up with 13.5 inch. So I know that this D is going to be 13.5 inch. I'm going to be going here at the distance, 13.5 inch from face of support. And then you find out the shear. Now we have better understanding now of the shear diagram. So if I give you here any two sections, this is now a discussion that you guys need to understand to figure out what is in here in this equation. If I give you here two sections, I'm gonna call here this is gonna be V1 and this is gonna be V2. Now where's V1? Please just stay with me. This is gonna be here V1. And this here is gonna be V2. How much is the drop from V1 to V2? If I tell you here the distance between the two is going to be equal to 1 foot, how much is the drop from V1 to V2? Can someone help me with this? This distance from here to there is equal to a foot from here to there. So how much is the change from V1 to V2?
Is it 2.92 kids per foot?
Exactly. Yeah. Because the shear diagram, it shows you here the change in the shear value, and the change in the shear value is going to be based on this W ultimate. So for each foot, when you move here to the right, you're going to be reducing the shear by 2.92 kip. This is the meaning of this uniform load. So if you look here at the face of support, the shear equals 29.2, right? Which is this value here. If you want to go to the shear here, you need to reduce it by how much? By 2.92 per foot. This distance is 13.5. So I'm going to say here 13.5 divided by 12 is going to give you the distance in foot multiplied by 292 subtracted off the 29.2, which means the shear from here to there. I can here write a general equation for you. I'm going to say here, okay, V2 equals V1 minus 2.92 times the distance. I'm going to say here, I'm going to call it here, what do you want to guys call it? The distance. I'm going to call here distance, like this. So what does mean by the distance here in this case? Distance is going to be the distance from this line to this line. So this is going to be here the distance. It's going to be this thing. It's going to be the distance from here to there, right? So the distance here between now and our problem, the distance from this section, from face of support to critical section of shear, 13.5 inch. So V2, which is the ultimate shear that we need to use in our design, is going to be equal to the shear 1, which is right at face of support, subtracting the distance, 13.5, 12 divided by 12, times uniform load 2.92. You're good?
Yeah.
Any questions? All right.
Where
Now,
did you get the 13.5 inches? Like, is the depth given?
oh, 13.5 inches, where I take it from? Very good question, Raman. Very good. I'm going to take you back here to this problem. In this problem, we have done it in the past. This is taken from previous slide set. So what we have done, give me a second. What we have done here, we say D equals 16.0 inches, right? Subtracting 1.5 inch. Do you know what is this 1.5 inch come from? Yes, Raman?
Cover.
Oh, the concrete cover, good. Then how about the tie? What is the side diameter of the tie?
For number 8, I think the diameter is 1 inch.
Okay, we're talking about the tie. Is the tie number 8 or the
It's a
longitudinal
number
bars
4.
number 8?
Oh, no, it's a number 4.
Okay,
So
and
it's a
number
half
4,
inch.
half inch, minus 1/2 of the bar diameter, longitudinal bar diameter. So number 8 is going to be 1 inch. Half of it is going to be half inch. How much is this? Can you help me with this?
13.5.
Great, okay. So what did I do? I was trying to find out the distance from here, center of this rebar, right? To where? To the top of the concrete, this distance here. It's equal to 16 minus 1.5 minus half inch for this minus half of this bar diameter. So actually it was not given, it was calculated. So the depth 13.5 was just calculated. Are we good? Yes? Questions? All right, I'm gonna stop here and switch to the homework. Does it make sense? What do you guys think?
Yeah, a lot better.
Wait, can you explain where the second 0.5 came from, please?
The second, which one? The second?
The second,
Second half inch?
Yeah.
Yeah, excellent. This one here, the diameter, this diameter is equal to how much? For number 4, half inches. And my target is to find out the distance to the middle of this rebar. This round shape that you're looking at, this rebar, is number 8. The diameter of this number 8 is 1 full inch. Therefore, the distance from here to there is going to be additional half inch.
Okay, thank you.
No problem. No problem. Any other questions on this example before I move to the homework? Can I move to the homework?
Yep.
Yeah.
Yes.
Okay. So in this homework here, you have actually two problems. It says problem A and problem B. So first, let me try to understand. It says here, when you have positive moment, do the following. When you have negative moment. What does it mean by positive moment? What does it mean by negative moment? Can someone help me with this?
Positive moment, you have compression at the top, tension at the bottom.
Good. And negative moment?
You have tension at the top, compression at the bottom.
Excellent. So when you have positive moment, where is the tension steel? How many rebars for the tension steel for the positive moment?
12?
Like
12, number 11?
Yes.
Okay. How about the compression reinforcing here?
20, number 11.
Exactly. How about here when you have negative moment? How much is the tension reinforcing?
And 20, number 11.
And the compression? 12,
Well,
number
number
12,
11.
number 11.
Good. If I did the analysis here at the beginning, I'm going to say I'm used to one section that we called here T section, right? But I don't see this. I don't see here a T section. I see section with a few webs. What should I do? I mean, this is going to be here complex. I'm going to say, no, it's going to be very simple. This section is equivalent to a T section, exactly a T section. Yes, second. Here's a T section, right? This is exactly equivalent to it. This width of the section is going to be equal to 6 feet, okay? The flange thickness, here it used to be 8 inches, now it becomes 6 inches. How about this web? How much is the width of the web in this case? You say width of the web is going to be 4 plus 4 plus 4 is going to be equal to 12 inches. So take this section here and do the analysis if this is here equals to 12 inches. Someone's going to say, but this is here 4 feet. I understand. This is going to be 4 feet when you have what? When the compression is going to be on this side. When you have this negative moment, you need to use this to be 4 feet. Not clear yet. So I'm going to say, let's see here item by item. How much is the effective depth of the beam when you have positive moment? Let's say effect depth, positive, the effective depth goes here from the tension all the way to the compression, right? It's going to be this distance. You guys agree? Yeah. Depth of the compression block, what do you call it? This is A, you say A equals AS times Fy. Now which AS? You can see this AS, the tension, right? Fy. Oh, I see, but you have here compression. Okay, now I need to stop. I cannot continue because I have also compression. So what should I do here? You say, all right, now you need to go back to this slide set. Which one? The previous one. I need to do something like this. AS1 and AS2. It's going to be exactly like this, but now I have a T. But you know what? If you find out that A, when you do your analysis, is going to be within the slab, it means that you have what? A rectangular section. Am I correct?
Yeah.
Yes.
So actually, this problem here should be simple because most likely A is going to be within this 6 inch. And you shouldn't have any trouble with it. Also, when you do the analysis for the negative moment, also A is going to be very small. It's going to be smaller than 4 inches. So actually, don't be confused by this weird shaped bridge, right, section, because what's going to happen, you're going to have rectangular section top and bottom. Just in case, what happened here if the anterior axis or compression block depth is going to happen right here? Say, okay, you're going to have here C1 and C2. This is going to be for C1, right? This area here times 0.85 A prime C. And C2 is going to be equal to A lowercase 2 multiplied by the total width of the 3 webs, which is 12 inches. Let me show you where this happens here. Talking about this case. when you have two compression forces, C1 and C2, or NCF and NCW, or like this case, right? Like in this case, we're gonna have here two compression forces, right? How do you find this A2 lowercase? First, you find out the compression force here, and of course the compression force in the steel, and then you find this out A2. But you know what's gonna happen? Most likely you're gonna have a case like this. So it's gonna look like a T section, but in reality it's gonna be a rectangular section and answers. Any questions? I want you guys, you still have here 10 minutes that you're talking. I want you to take maybe a couple of minute break. Think about any questions related to this homework. Do not expect that I'm going to be able to answer you late Sunday. Advise you, here's one advice. Try to do a quick spreadsheet to help you out to solve both of these two problems. Because whatever that you do in the first one, you're going to be repeated exactly in the second one. So if you do a quick spreadsheet, it should be done very quickly.
Professor, quick
Yes.
question is,
Yes.
are all the lectures online up to date? I'm looking at the YouTube. I just want to make sure if all of them are here.
You tell me.
Yep.
If all of them.
Oh, sorry. Yep.
You're good?
Yep.
All right.
Thank you.
Very good. All right. Now, please ask me questions about this. I want to be sure that you guys are covered for this homework.
Professor, what is a positive moment again?
A positive moment?
Yes.
Okay, let me write it here. So I'm going to say here, in positive moment, tension at bottom, right? Compression at top.
Got it. Thank you.
About the negative moment?
It's a
The
positive.
other way around. The
Yeah.
opposite of this.
Thank you.
No problem. I'm waiting for questions. I want to be sure that you guys are covered with this homework.
Can you explain how this is related to one in which the cross-sectional area had resulted in two compression forces?
Let me put this on. We're talking about this example here, like in this example, right?
Mm.
This one you have two compression forces. So like in here, this is exactly what you're going to have in this problem. You're going to have two compression forces. One is going to be going to the concrete slab, and the other one is going to be going to the compression steel. And then you are going to have tension here for the tension steel. So say, okay, what are these forces? Here is one compression force. It's going to be where? Right in the mid-height. This distance from here to there is going to be 3 inches, right? You see the distance here? This is going to be right in the middle of the slab. So the compression in the steel is going to be right here. I know the location of it. And the tension in the steel is going to be right here. It's going to be tension here, right? How about the compression of the concrete? You say, well, compression of the concrete is going to be really based on the depth of the compression block, lowercase a. How can I do this? I'm going to say, well, let's say this is going to be the lowercase a block depth, right? It's going to be up to here. And this depth here is going to be equal to a. So let me take this and do quick shading to it. I'm going to say, okay, let's put this light color here. Okay.
And this is the one where you're saying where A will be within the 6 inches, resulting in a rectangular section?
Yes.
Okay.
Yes. So this depth here is going to be equal to A, depth of compression block, right? So the depth of this shaded thing is going to be equal to A. If the total depth here equals to A, is going to be the depth, right? Therefore, the compression force is going to be where? It's going to be at A over 2, which means roughly it's going to be here. So this is here what we call C1, which is for what? It's going to be for the compression of the concrete, right? Which is the top one here. And then I'm going to have here C2. C2 is going to be right here. It's going to be compression in the steel, which is going to be this guy here. How about the tension force? It's going to be just one tension force. What should I assume for the tension force? I'm going to say assume that this tension force is going to be at yield, which means Fy of 6 KSI times 12 times, how much is the cross-section area for number 11 bars? Can someone help me?
1.56.
Yeah, equals, and then you can put the number. This is going to be the tension force. So assume that the bottom steel here is yielding, you do your equation, and then you're going to say this is going to be equal to. And then at the beginning, you say, do you think that the steel on the top is going to be yielding? You say yes, and then you try your numbers. Everything works good, because also you need to check the strain, right? You need to do the strain analysis. You need to figure out how much is the strain top and bottom. Why do you need the strain top and bottom? Because you want to double check and be sure that the strain, that the steel top and bottom is yielding. If both sides are yielding, your assumption is good, you just continue your analysis. If the top is not yielding, what do? Here's what you need to do. You do this equation, right? You just use this equation. This equation, you have here two unknowns. You have the C and the strain in the steel, or the stress in the steel. Which slide set is this? Oh, it's slide set number 6. This one you have compression reinforcement.
Wait, quick question, Professor.
Yes.
For that one, you know how like you're like if one of the assumptions are wrong for like the steel yielding for compression or tension, you go back to that formula. Do you have to? Do we still have to like after once we get that? Do you still want us to verify that the new assumption is correct?
Yeah.
Okay, so you'd still prove it even after like the correct equation.
You find out the strain because you need to find out the strain.
Right.
So, and this is what I'm saying here. Be sure that you have a quick spreadsheet to do this for you. I mean, you cannot repeat doing the strain thing here like 100 times, right? Just do it for yourself. Keep it there because every time you're going to be doing it, you have done it already for the rectangular section, and you're going to do it here, and you're going to have a project that you're going to repeat it, right? So you're going to keep repeating this. Just have a quick spreadsheet to do it for you. The spreadsheet will take care of doing this equation, right? And it's going to be also doing this analysis for you for the stress and the strain in the steel. So let me show you what I'm talking about. Like in here, you see this?
Yeah.
Just do it in a very quick spreadsheet so you don't have to think about it every time. It's going to get here the strain in the compression steel, the strain in the tension steel. So once you have C, all what you need to have is C and D. Once you have C and D prime, figure out the strain in the compression steel and tension steel. Quick.
Thank you.
No problem.
Last question.
Yeah, go ahead.
Can we, oh, okay.
No, go ahead. Anyway.
Can we say that, generalize that whatever we assume, then we have to verify it at the end?
Yes, absolutely.
So if for that one, first of all, we assume both compression and tension steel yield, and then we have to verify if both of them yield or not.
Yes.
So, okay.
Yeah, Jacqueline?
My question is when you do the negative moment, and we know that tension is on the top now and compression's in the bottom, does that mean the tension is still 1 force and the compression will be 2, or would it be different?
Yes, absolutely. You just flip this. Yeah.
Okay.
So, yeah, you just take these 2 forces, put them on the bottom, and this tension force, put them on the top.
Okay.
Professor, for the negative, for when we do negative moment, wouldn't we treat it as a rectangular section for compression?
For the negative moment,
Yeah.
it's going to be exactly the same thing because now this becomes like a flange. So this is going to be equivalent to a T section. It's going to look like this. Because on the top here, this width is going to be equal to this plus this plus this is going to be 12 inches. At the bottom here is going to be 4 feet. Now this becomes T section. So if you do your analysis and you're trying to find out A and A turn to be within this slab, which means in this case in the negative, if A is going to be less than 4 inches, then you have a rectangular section.
So we have to like rotate the flange, or because I don't like, I see how it's a T section in the top, but in the bottom I don't
Okay.
see.
Okay, you don't see the T section, right? That's what you're saying. All right, your section is composed of 3 pieces here. Let me do it here in separate column. Let's say, let's put it here in this column. Okay. I have 3 webs. You see here 3 webs, or you see only one? This is like a hole. You understand this symbol, right? Yes? Or
Yeah.
no? Okay. So if I want to do this analysis for a beam like this, and also it has some concrete here in the bottom for this slab, so I'm gonna make it this way, right?
Oh, okay. I see now.
Okay. So all what I'm saying is just convert it into a T section. How do you do this? You bring this here, and then you bring this here. Now look at the shaded area only. So you have a T section. Okay? This is what I'm saying. And the total width of it, the width to the width is going to be 4 plus 4 in the middle plus this 4 inches. All right. You guys, if someone wants to sign out and go ahead, please. If you have more questions, you just stay around and ask.
Thanks, Professor.
Yeah.
Okay.
Thank you.
No problem. Good night.
Will you be able to upload this lecture and Tuesday's lecture
Yeah.
this week? All right. Thanks so much.
Like in a few minutes from now, 10 minutes.
Okay. Perfect.
Professor.
Yeah.
When calculating for problem B, the negative moment, do we just like rotate the?
Yeah. Just put it upside down. Absolutely. You do it this way.
Okay, and then we'll consider like the tension.
You do it like this.
Exactly.
Yeah, exactly. You just rotate the piece of paper and then you say this is gonna be compression, this is gonna be tension here.
Okay, perfect.
Yeah.
Thank you.
No problem. Any other questions? Okay, you guys have a good night.